Okay everyone, let's go ahead and take a look at implicit differentiation. Now before we go over and talk about how to implicitly differentiate, let's determine where implicit differentiation rests within differential calculus. Now, what we've been dealing with before implicit differentiation is just straightforward differentiation of functions. Now the thing is though, is that functions are a subset of relations. So what happens when you come across something that is not a function? How do you go about differentiating something that is a relation and not a function? So what we have then is implicit differentiation. So implicit differentiation in short is going to be the means by which you go ahead and differentiate relations. Now there are a couple of key facts that we want to keep in mind. All the rules for differentiating functions still apply when we differentiate relations. Okay? B, when differentiating implicitly, the chain rule is most important. Okay, we'll go ahead and take a look at a couple of examples, and let's start off with this first example here. Now take a look at this right here. Now of course this is y is equal to 1 over x, the reciprocal function, and we know that it is a function. So what we'll do first is we'll go ahead and differentiate as it is a function. Now notice what we're doing is we're differentiating both sides, and we're saying that the derivative of y with respect to x is d of y over d of x is equal to, we're using the power rule here, this is negative 1 x to the negative 2, and then so we can go ahead and conclude that d of y over d of x is equal to negative 1 over x squared. Now let's just go ahead and just change the form just slightly, and notice that if I multiply x to both sides of this original reciprocal function equation here, I'll come up with xy is equal to 1. Now notice it's exactly the same, and so when we differentiate, we should still come out with the same result. But notice that being that the form is a little bit different, we're going to have to approach this very slightly, and this is the way that you differentiate implicitly. So when I take a look at this here, I got two variables, one is x and one is y, they're being multiplied together. And being that the case, I have to use the product rule. So if I use the product rule, I hold this one constant. I take the derivative of y with respect to x, and notice that that's what that is. Plus, I take the derivative of x, and I come up with 1, times it by this value, the value here, which I keep constant, which in this case is y. And then that's going to be equal to the derivative of any constant, which is 0. So notice that what happens then is I can say that x times it by d of y over d of x is equal to negative y, because I can move that onto the other side. And notice that what I'm trying to do, of course, is I'm trying to solve for d of y d of x, because that is the derivative. So notice that what I come out with then is d of y over d of x is equal to negative y over x. So notice the difference here. The derivative now is in terms of both x and y. When we actually took a look at what happened when we differentiated the function version of this particular equation, we came out with the derivative in terms of just x. So that's a very key element and a very key difference between the results of implicitly differentiating and differentiating a function. Now, the thing is that we still know that y is equal to 1 over x, because we know that that was the original function, that was the reciprocal function if we wanted to go ahead and solve for y. So what I could do is I could then go ahead and substitute that value into here, and I can come up with the expression of negative 1 over x squared, which is exactly the same expression that I came up with the derivative when I had it originally in its functional form. So again, notice that even if we start off with something that looks not like a function, or more like a relation, we can still go ahead and come up with a consistent result just by making sure that we can substitute in the value of y in for something in terms of x. Okay, so the results are the same. The results might look a little bit different, but they're the same. Now, let's go ahead and take a look at a little more complicated situation. Example number 2. And this says x squared y squared plus y is equal to 3. Now why is it that this particular situation is a little bit more complex? It's not because of the fact that we just have more variables there, but it's because we cannot solve for y. We cannot explicitly write this as a function. So therefore this is a relation, and it's going to be strictly in this area here when it comes to the set relationship between functions and relations. So I still go about doing the implicit differentiation using the rules of differentiation exactly the same way. Now notice what I have here. I take the derivative of, I have a product here of x squared and y squared, so that means that I have to use the product rule. That means then that I have the derivative of this, which is 2x, times it by the hold this constant, which is y squared, plus I hold this constant, and then I take the derivative of this. Now I have y squared here. So if I take the derivative of y squared, well, that's the power rule first. So that's going to be 2y times it by the derivative of y with respect to x. And then notice that I have plus the derivative of y with respect to x, because that's what the derivative of y with respect to x is, equaling 0. So what I have now is, if I go ahead and just rewrite this very simply, what I'm trying to do again is try to solve for d of y over d of x, which is the derivative. So I go ahead and combine all of my terms that have the d of y over d of x. I take all of the terms that do not have d of y or d of x onto the other side, and I come out with this. And then after that I just divide out by whatever the factor is that's being multiplied to d of y over d of x, and you then find your derivative. So notice that in this case over here, the derivative is in terms of both x and y, and I can't see any possible way of actually changing that form of the derivative so that it is only in terms of x. Maybe you can. Okay? So there you go. Let's go ahead and kind of wrap things up again with regards to implicit differentiation. Implicit differentiation is used in particular for differentiating relations. It can still be done for functions and you'll still come up with the same result, but primarily it is used for relations when you cannot explicitly solve for y in terms of x. So notice that the difference that comes out in terms of the form is that your derivative will be both in terms of x and y. Okay, so there you go. One last question though before we go ahead and move off. Here's the derivative of this particular relation. And notice that it's in terms of x and y. Here's a question for you. What would the second derivative look like? Okay, so go ahead and take a look at that. Think about that. Maybe you want to give that a challenge. And we'll talk about it tomorrow. Okay, see you later. Bye-bye.